Well, good evening, everybody. As you can see, the clock has run out. My name's Steve. I guess I'm your MC for the night. So anyway, welcome to the meeting here. Let's just go ahead and get going, and I will forward the slides. So give me a second here, and let's go over here. And there we go. Okay, it's going to take a while. I'm going to take this out because I don't like it. All right, so we are at the meeting call to order, which is you've all taken your seat. You've all quieted down, so thank you very much. We're happy to have you here. Next up will, of course, be welcome, and then we have a few announcements tonight. We have our standard general announcements that I'll get through as quickly as I can because you've heard them before. But we do have some special announcements as well regarding equipment and some other things that are happening. As you can see, we also have a member presentation a little bit later, maybe 15, 20 minutes from now. We'll be seeing that. And then we'll do our seventh inning stretch. Get a chance for a few minutes to socialize, stretch, get some water, use the restroom, whatever it is you need to do. And then we'll have our speaker, who is right over here, Dr. Jenna Moore, and she's out of ASU, and she'll be talking to us about some stuff coming out of Atacama, Chile. So there's kind of tonight's agenda. So let's go ahead and get to the welcome part here. So first of all, to everybody in the room, welcome. And to those that are on Zoom, and James says we have several people on Zoom, welcome to you folks as well. We thank you for being with us here tonight. We are thankful for that. As always, we hope you enjoy yourself. We hope you learn something interesting. We hope you make a new friend, and we hope you can reconnect with old friends while you're here. So that's the idea tonight. Welcome to everybody. Now, here's the part where we say, do we have any visitors with us tonight? And if you do, you can put up, I got a couple of hands. So, all right, we're going to make this really simple. We are going to give you a microphone, nothing embarrassing here. You can see right on the screen kind of what we're looking for, your name, how did you find us, what reason brought you here, etc. And go for it.
Yeah, Dennis Bernard. I had been a member before, but maybe I'll join again. And I enjoy coming here to the lectures.
Okay, all right, James. And back in the corner here.
I'm Mike Mickek. Actually, I was with the club when they were up in Scottsdale Community College so many moons ago. I just getting back into astronomy, so I got an 8-inch and I'm learning all about it. And I got a new mount, so I figured no better place to come to the club here and join in. No, that's about it.
Well, thank you both for being here. Welcome sort of back in a sense. We have one more visitor as well.
Hi, my name is Betsy Sevillano. I'm here for the rare occasion to spend an evening with my husband when he's not with his mistress, Stella Celestron.
Okay.
My favorite thing in space is the nebula Bohr's helmet.
Okay. All right. Well, welcome to you as well. So I'm anxious to hear your husband's presentation tonight. So that'll be kind of fun. All right. Well, thank you all for being here. We have our standard general announcements. I'll get through them quickly because you see them pretty much every month. And then we do have a couple of special things along the way as well. First of all, regarding joining or renewing your membership, as always, Brooks is on the back table back there against the wall. If you turn around, you can see him, unless you're on Zoom, of course. And so you can renew or just get a brand new membership from Brooks at any time. If you look at our website, though, and there's a screen capture from it, you can also do it from mail, and you can also do it through PayPal and do it through online forms and stuff as well. So there's numerous ways to join if you would like to do so. Notice that up in the top corner of the screen there's a blue button called New Member Guide. If you were to click on that on our website, it does bring up a little PDF, looks something like that, which tells you what it means to be a member, kind of what's involved, what do you get, what do you do, with all those sorts of things. Matter of fact, there's a link at the bottom of almost every one of the web pages that says New Member Guide, and you can click it and get the same form. So anyway, that's available to you as well. If you would like to know what's happening at any given time here at EVAC, you can also, once again, go to our website, go to the home page. And if you want to, you can click subscribe there. and that will get you onto our mailing list. And it's not a spam machine. You'll probably get 3-4 emails a month tops, most of them announcing this meeting, or if there's anything special that's going to be happening, like a big star party or something, it would be announced. So it's not a spam machine. It's not going to overrun you with spam. And we do not sell your email addresses to anybody else. So it's joining us doesn't mean you're suddenly on 30 other mailing lists. So don't worry about that. However, if you still would not like to do it that way, you can always go out to our website, and on the events and meetings page there, you can see there is a calendar, and on that calendar for the month would be anything that's happening that month here at EVAC. And so a couple of people at the club here keep that up to date. So that's available to you as well. Also on the news and resources page, there is a newsletters link. Every month we do put out a newsletter. It also talks about things that are happening that month as well. So there's many, many different ways to find out what you can be involved with here at EVAC is what it is going to be. James, you're going to be talking here in just a moment. So why don't you just come up here and talk, since this is your forte.
Do I need to go to the next slide, or is this it?
That's it.
Okay.
So,
yeah, so just to remind you guys, we do have the rental program going, and we recommend checking it out on our page there. We've got a nice 10-inch stop. We got an 8-inch go-to Celestron, Smith Cassegrain. We also have the, we have this Seek Star, the little imaging thing that's going for $500. That's selling like hotcakes. It's pretty nice, pretty easy to run. So all that stuff is only $25 a week to rent if you're a member. So contact me and we'll be happy to get you some of that gear.
All right. In addition, if you'd like to learn a little bit more, so we'll have James back up here in just a moment again as well, but out on our website, if you would like to do some reading, learn more about astronomy, how to run a telescope, things like that, you can go out to the news and resources page. There's a link out there to the virtual beginners lab, and every one of those blue boxes you can click on, and it brings up that little PDF or a web page on that particular topic where you can actually learn a little bit more about astronomy along the way. In addition to that, though, we have some online classes or hands-on classes coming up, and James is going to talk about that in just a moment. One of the charters here at EVAC is to give back to the community. It's to educate the community, give back to the community, do those sorts of things. So a couple different ways you can do that. As always, we do have an observatory about 100, 150 yards that direction. And you can volunteer to operate the telescope, do crowd management, anything you want to do at that observatory. And so we have a whole list of guys. And what happens is every month, an email goes out and it says, are you available next month or not? And if you're not available that month, you just say, I'm not available, and you don't get scheduled that month. If you say you are available, then you usually say, well, I can do anything but this Friday or that Saturday or whatever it might be. And then they build a schedule and it accommodates your schedule. But you can be a telescope operator, get involved and do some things. And I know half the people I know in here are from working over there at the Greco. It's a good way to meet people in the club. So I see some people smiling at me right now because they know me from over there as well. So anyway, also on the second Friday of every month, if you want to bring your own telescope and set up in the grass over there outside the observatory, you can actually have people look through your telescope or whatever you'd like to show them as well. So we have that second Friday of the month public star party. In addition to that, we also do private star parties around the East Valley here, really almost the Southeast Valley, where we go out to schools, HOA, science centers, things like that, and we do little star parties for the public. So if you'd like to be involved with that, notice there is a place you can kind of sign up to get on the email list to find out when those events are happening and volunteer your time and your telescope for those sorts of things. I will mention, though, that the private star parties are winding down. I think we have one more scheduled in early May, and that's pretty much it, because two reasons. It doesn't get dark till late, and so it's hard for schools and stuff. And then the other thing, it's hot. It's just hot. Those of us that work Greco during the summer, we all know it's hot. So anyway, so we don't have a lot of private star parties this time of year, but during the fall and winter and early spring, we're quite busy with star parties we could always use to help. So anyway, that's a way to get involved. Why join in? As always, it feels good when you give back. Helps you to learn more about the sky and telescopes and so forth, and helps you to build friendships as well. All right, special announcement. This is going to be you, James, again. So come on up and.
Okay. Before we do the announcement thing, just to also remind you guys, we periodically, some astronomers will go out to, thank you, go out to pickup posts. And the way you learned about that is make sure you're on the announcement distribution list. Because if you're interested in going out sometime, we probably will do one more near the new moon coming up in May, and then it'll be too hot. So announcement. So we are going to have a beginner's guide to small telescopes class that I'll be teaching starting in early May. It's only $15 for members, $25 for non-members. If you don't have a telescope and thinking about buying one, this is a good way to go. Or if you have one and just want to learn how to use it more and understand more about the basics of astronomy, this is a good class for you. It's 5 classes that are in Zoom sessions. So 5 Zoom sessions on Tuesdays at 7 p.m. And starting May the 7th. It'll be at once a week, 5 sessions. They're recorded, so if you miss it, then you can always come back and watch it later on from the website. And then there's also 5 telescope hands-on sessions starting that Saturday. It'll be every Saturday at 8 p.m. The location of the labs will be different depending on what the phase of the moon is. We may go out to picket posts if it's near a new moon, or else if it's a full moon or something like that, we'll probably just have it at the observatory out here. So if you're interested, make sure you contact me by Sunday because we're trying to get the number of people that are going to be doing it listed up. Here's the email address is jtyastro@artcentrics.com. There's also, if you want to find out more about the class, here's the URL. It's tinyurl.com/EVAC-class 101. And you can find out all the details and the materials on there also. So you're welcome to take a look at it. Okay. On to next.
All right. Good deal. All right. Thanks, James. Not a bad deal if you want to get into a class. If you do the math, it's $3 a class if you're a member and $5 a class if you're not a member. So it's horribly expensive, but no, I'm kidding. So $3 and $5. So anyway, all right. Good deal. Once again, if you're happy to have this club and you like joining and you like being in the lectures and meeting people and talking shop with telescopes and astronomy and so forth, there's a number of people. I'm just going to bring them all up here really quick on this screen. These are some of the people that are helping out with everything. So when you run into these people, say thank you, because some of these people do spend a lot of time trying to keep things running here. Like Brooks, you know, he's always doing something with the bank or insurance companies or trying to make sure our BLM land is all taken care of so we can go out and do our star parties. Or Woody's always trying to find speakers like Dr. Moore here. And so a lot of these people do a lot of work. So thank them if you do run into them. It's good to have this club. I really enjoy it. And I'm happy for every one of these people here. All right, let's see what else we have here. It is now time for a member presentation. So we see Evelio's coming up here right now, and you can just hit the forward arrow and you're up.
Okay. Thank you. So my name is Evelio Sevillano, and I'm enjoying astrophotography from my backyard. So today I'm going to share some of those pictures. But we will also answer a couple of questions. First of all, what can we see out there from using a relatively small telescope? And we'll also learn that most of the visible universe is in the plasma state. So what is a plasma and how do we use plasmas on Earth? So what is a plasma? Plasma is the 4th state of matter. Solid, liquid, and gas are the other 3. And each state has specific properties that make it unique. A plasma is a gas where the electrons have been stripped off the gas atoms to form a mixture of neutral and charged particles. We have what is called ionization. We have an ionized gas. And this ionization is often the result of adding heat or other sources of energy, microwave energy, radio frequency energy, ultraviolet light. And because charged particles respond or are, when you have an electric and a magnetic field, those affect the particles that are charged. The gas mixture the properties of that gas mixture that's partly ionized is fundamentally different than anything else, and therefore you have a different state of matter. We can also manipulate the electromagnetic fields to make the plasma do things that we might want it to do. And so that's why, and we will see a few examples of why they're important and how we use them. The sun happens to be the largest plasma in our neighborhood, right? So everybody sees the sun every day, at least here in Arizona most of the time. And it turns out that over 99% of the visible universe is in the plasma state. So plasmas are very important for life. Obviously, the sun, the radiated energy from the sun, and sun is going fusion, hydrogen fusion to generate the power that we get from it. And Earth is located in just the right spot to have liquid water as a normal occurrence. Now, this picture is not my picture, but you can see how the flares have those arches, and those are a result of the magnetic fields in the sun affecting the plasma and the corona. And so you see how the plasma follows those magnetic fields. Plasmas are also important for energy generation. And this is a cutout of the ITER tokamak that's being built in France. And the idea is to have the same process of the sun, but controlled on Earth, and create mini suns that would enable us to generate inexhaustible energy, really. No limit to how much we would do. The problem is that confining a plasma at the high temperatures that we need to create to have fusion for long enough is a very difficult and a huge technological challenge. However, we need to continue to pursue, and this tokamak is under construction in France. I want to point your attention to those D-shaped coils of the donut. The plasma is that pinkish thing, and is shaped in the form of a donut, and you have those D coils. And to give you an idea of the size of these machines, here's a picture of one of those D coils after it was built by Toshiba in Japan. And you see on the top the size of the entire Japanese engineering team that built this coil. They need 18 of these coils to power the magnetic fields in this machine. And that's only one subset of coils. Now, plasmas happen to be also very important in semiconductors. They're widely used in many semiconductor manufacturing processes to make all the advanced logic in your cell phones, in your computers, in your data centers, and the memory devices that are there. And plasmas are used to make to either deposit or etch the layers that are needed to make semiconductors today. And that's a picture of a 232-layer NAND flash, and NAND flash is the memory that you have in your thumb drives and solid-state drives. And to give you an idea of the size of these devices, here's 2 human red blood cells stacked on top of each other. And that's how big these things are. The things that we carry around, 2 red blood cells. Pretty impressive. Now, plasmas happen to be also important for growing diamonds. And this is something that I did a number of years ago. And today there's multiple companies growing gems using a mixture of hydrogen and methane and microwave power to get to this plasma. And you grow the plasmas very similar to the way pearls are grown. You have a seed, a diamond seed, and then you cultivate the gems. You grow them in the reactor. And the gems that you come up with are actually identical to mine stone, but the shape is more controlled. So now you can cut and polish and always have an ideal cut if you so want. They're also conflict-free and environmentally more friendly than mining. And if you want to see some of these diamonds, my wife is there and she's sporting some of these. In terms of equipment, I'm not going to go through this in detail. Basically, it's a celestron. This is Stella Celestron, and it's 9¼ inches, and the usual paraphernalia. But it is automated, and I'm able to run this from the comfort of my office in air condition or heat, depending on the situation. So 99%, over 99% of the visible universe is a plasma. So what can we see? Obviously the sun, the solar system, our neighborhood. Solar system is the main plasma in our neighborhood. My interest lies in deep sky objects. And these come in two flavors inside the Milky Way and beyond the Milky Way. And inside the Milky Way, stars, of course, all the stars that we see with our eyes are part of the Milky Way. But nebulas are also very interesting to me, and they're coming in many flavors. And I'll be going through a gallery of different types of nebulas as we go through the talk. Outside the Milky Way, we see galaxies. And of course, they also come in multiple shapes. But we also see stars in those galaxies, which to me is rather amazing that with a little telescope, I'm able to see this. And this is a picture of Thor's helmet. It's an emission nebula. And the way these pictures are generated is they result from stacking many single exposures that are taken with a camera, basically an astronomy camera. And each exposure, in my case, is about 4 minutes. To get a picture like this, for example, requires about 157 frames. Some you have to throw away. So you can do the math, is a 10-hour type of thing. The software that I use is PixInsight, which is very powerful. And within PixInsight, you can stack all the individual pictures and then expand the color range and so on, so you can get the pictures that you see here. It also has a very powerful color calibration system which uses the colors of the stars in the foreground to actually get you the calibrated color of the camera. So that's very, very powerful and interesting. So if you want objects in detail, you got to spend the time. Basically, that's the bottom line. You got to get the signal to noise correct. This is a picture of the bubble nebula, and these are called H2 regions. This is, again, another plasma. And it's red because it contains mainly hydrogen. The previous picture, which has a lot of green, the green comes from oxygen emission. So that plasma that you saw in the previous picture has oxygen and hydrogen. This one is mostly hydrogen. And what is interesting is that hydrogen in space can exist in the atomic space because there is very little interstellar density. And whereas on Earth, we always find molecular hydrogen. So hydrogen atoms in these H2 regions are ionized by UV light from the local stars that are around. And these regions can be quite large. And one example of such a region is the Great Orion Nebula. This is, the other thing, by the way, that in nebulas is that they're star-forming regions. And the Orion Nebula is the largest star-forming region closest to Earth. It's only 1,500 light years away, and it's 24 light years in diameter. This picture with my telescope requires 4 mosaics to be able to capture the nebula in its totality. So this is 4 mosaics, 30 frames each, 3 minutes long. This particular nebula is pretty bright, so you don't have to spend the 4 minutes. I was able to take these pictures in 3 minutes. Now, this is a cool one. It's called a dark nebula. It's the horse head because it has the shape of a horse. At least you need some imagination, but I think you can get it. And a dark nebula is a region where it's a higher density of dust as well of gas. And it's so dense that it kind of blocks the light coming from behind. And so they look dark. What is interesting about this one is that it's backlit by an emission nebula similar to the ones that we saw before, the red ones. And it has on the lower corner, on the lower left corner, it has a reflection nebula, a star that's very bright, and you're reflecting light from it, a little bit like the sun with the sky. You get scattering and you get a bluish reflection on the image. Now, we move to planetary nebulas. And planetary nebulas, when they were first discovered, they were thought to be planets out there. And of course, that wasn't the case. In fact, planetary nebulas are the result of stars that have run out of fuel and explode. And in this picture, you can see the outer, the first shock wave, if you would, of the explosion, you can see it beyond the main body of this nebula. And this is the Dumbbell Nebula. And in the middle of this nebula, what is left behind is a white dwarf, a dwarf. And a dwarf is a very interesting object because you have to imagine that you take the mass of the sun and you put it within the diameter of the Earth. You get a white dwarf. The density of that object is unimaginable. We won't talk about black holes, but it's extremely high density. Headphone Nebula, another interesting one. The reason I took pictures of this one is this one wasn't so easy. I had to spend a long time because it's not very bright. And some of these explosions, the same origin, a core that explodes, some of these explosions are fairly symmetric. You see here that it's almost round. Dumbbell Nebula has kind of two fronts looking like a dumbbell. So some of the explosions are different. And so there is a whole variety of these planetary nebulas that have different shapes as a result. And this one, it's called Jellyfish, is the result of an explosion of a supernova. And this particular nebula is, again, 4 panels on my telescope, but this one is 5,000 light years away. If you recall that the Orion was 1,500 light years away. So this object is about 4 times larger, and that one was already 24 light years. So this is about 100 light years across, a huge explosion. So the way these come about is that when you have a sufficiently heavy star greater than 8 times the mass of the sun, when they run out of fuel and collapse, and by the way, they can run until they get to iron because they're heavy, and they run fusion all the way to iron. When they collide, once they have run out of fuel, they're pretty large to begin with. 8 times the mass of the sun is pretty big. They explode in a way that releases a huge amount of energy. Now, my favorite supernova is supernova remnant is the Crab Nebula. And the reason for that is that this one was a nebula that was observed in the year 1054 by Chinese astronomers. So we know exactly when it started. I think in the last meeting, I think we saw some of the time-lapse photography on this particular one, which is very cool. So this one was visible during the day, in the year 1054, and it's about 6,200 light years from Earth. And this one has a neutron star in the middle of it. Now, it's always interesting to see if what you're doing with your telescope is, are you processing the data right and so on? So then you have to compare to the James Webb picture. And so, you know, I don't know about you, but I kind of see the same kind of structure in there. Now my colors are different because I use a dual band filter, green and red. The James Webb is actually looking in the infrared, so it doesn't have to look exactly the same. And so, but it's pretty amazing to me that all the structures are in there. So I'm not really doing anything wrong with the astrophotography. It seems to be working. So it's pretty cool that I can do that. So now we move outside the Milky Way. We go to galaxies beyond the Milky Way. This is one of my favorites, the Whirlpool galaxy. And it's about 31 million light years, which really, and if you look at the picture, you can see dust lanes, you can see conglomerations of stars. I can imagine nebula in this galaxy 31 million light years away. Now, you have to spend a little more time. You have to stack maybe 250 frames to get pictures like this, but it seems to be worth it to me anyway. And then this one is Fireworks Galaxy, a little smaller than that one. It's only 22 million light years from us. And again, you see dust and so on, but this one, when I took a picture, it seems really angry. I mean, there's a lot going on in this one. Turns out there have been 8 supernovas from this galaxy in the last century. So in 100 years, 8 supernovas happening here. This sucker is super active. Then Pinwheel, another one of my favorites. This one is about twice the size of the Milky Way, about 170,000 light years across. And Again, dust lanes, you have to be patient, 300 frames, dust lanes, stars, that you see star formation, new star formation regions where there's a lot of stars. But what's cool about that one is that last year, there was a supernova explosion in this galaxy on May 19, 2023. And I was taking pictures, and on May 24th, I get an email from Bob Buckheim. Says, have you been taking pictures of M101? I said, well, I took pictures yesterday. Well, look at them, because there is a supernova in M101 that wasn't there before. Oh, really? Okay, so there we go. You see there that on the right side of that circle, you see a star that's not present the previous month. And that was a supernova. My only, disappointment is that I was there May 23rd. This guy took pictures on May 19th, beat me by 4 days. But, so to close, we have learned a little bit about plasmas and why are they so important. The prospect of inexhaustible energy is really amazing. To me, the vastness, the complexity, the beauty, the strangeness of the universe are really beyond comprehension. And I want to say that in astrophotography, patience is a virtue, because the more times you spend taking pictures, the better the signal to noise and so on and so forth. So be patient if you want to do this. Thank you. Yeah, any questions, of course. There's one.
I just wondered, what part of the valley are you taking these from?
So I'm in Superstition Mountain on Gold Canyon. So it's if you look away from Phoenix, it's pretty nice. Down the street, and I stay above 30 degrees or so. So even if I have to go down to Phoenix, I stay in the sky that's a little bit better. Yeah, and with the nebula is pretty cool, because you have narrow band filters, and you can take pictures even when the moon is out. So those are easier to do. With the galaxies, you gotta kind of do them. It's better to do them at new moon.
Do you have any thoughts on the nature of dark matter, whether it's plasma or maybe there's a new material there?
Well, yeah. So my thoughts on it is clearly not a plasma, because we would be able to see it, and so it's likely to be something else. Now, the jury's out as exactly what it is. Dark matter, I don't think we know what it is. But it wouldn't be surprising to me if you get far enough outside of the galaxies that you could imagine a lot of remnants of explosions, that things have cooled down and you have material left out there. And that would be a possibility. In my mind, as a physicist, it doesn't have to be a different set of materials necessarily. It might just be what we know. It just happens to be not glowing. Thank you. Oh, one more. Two more.
Photography question.
Yep.
You're shooting these, some of these have taken over 10 hours to shoot.
Yep.
Actual time.
Yep.
So do you shoot those more than one night?
Yep. Yeah, sometimes if you look at the one, the pinwheel was taken over 4 nights. Now, fortunately, things don't move that much night to night. If you're taking a month apart, you probably need to re-register, use one of your older pictures and tell the software, I want the same angle and so on, because you might have rotated. But within a few days, things are pretty stable.
So what do you use for stacking software?
PixInsight.
What was the model of your camera?
The what?
Model number of your camera?
It's a ZWA ASI, the MC533 Pro MC. So it's a one-shot camera, one-shot color. Sorry, is ZWO the ASI 533. $800.
do you use any filters for the broadband?
So I have a filter, but it's the L Pro, so it's fairly broadband. The Ortholong, that's what I use in that type of photo. So a lot of the color comes through, but it helps a little bit with the background lights.
All right, thank you very much. Thank you.
I had one more announcement. Also, we also have a equipment sale. We also have an equipment sales page, and the tiny URL for that is tinyurl.com/EVAC-sales. We also are starting to sell some equipment from the community. So for instance, if you have a telescope you want to sell, you could contact me and I can post it on the website and you could sell it there. We're charging $5 a month for that. Also, just a heads up to you guys. I know a lot of you have telescopes already. We've had unfortunately, a couple of deaths in the astronomy community recently. And so I know there's going to be a lot of equipment coming on shortly. I'm supposed to go inventory it for them. And I think the families are going to try to sell the equipment. So that keep an eye on that page because there's going to be some gear from astronomers who've done it most of their life. So some probably pretty decent gear coming up. So that's all I had.
We are now officially at our break. So we're going to take a 15-minute break. Let you socialize. Are we on? Okay, everybody. I hope you enjoyed the break and had some chance to talk. We are going to move on to our main presentation here tonight. And so I'm going to let Woody go ahead and introduce our speaker, and then we'll see what she has to say. Thanks.
Hello, everyone. Thank you for coming tonight. It's my privilege to introduce freshly minted Dr. Jenna Moore, who got her PhD in astronomy and astrophysics and telescope engineering and a lot of other interesting things at ASU. And she's going to talk about the Simons Observatory, correct? And Jenna, welcome.
Well, thank you. Thanks for having me. Tom Marsden, who's not here, kind of ambushed me right after my defense. Oh, do I need to hold? I probably got to hold this maybe. Anyways, Tom Marsden kind of ambushed me immediately after my defense and was like, you must come and give this talk at EVAC. So I'm very happy to be here. I'm very happy to be at a local astronomy club. My first experience with the telescope was at a local astronomy club meeting in South Carolina. I kind of have taken a very roundabout way to the job that I'm in now. I started as a chemist and then I dabbled in physics, and then I came here and decided to help build some really cool telescopes. And so I'm going to talk to you guys today about the Simons Observatory, which is a project that I've been a part of since I started as a graduate student at ASU in 2018. I'm still working on it now as a postdoc, and I've been lucky to kind of see the whole thing come together over all these years. All right, so a little bit more about me. I have a PhD as of a couple months ago. I'm still getting used to people calling me Dr. Moore. It's a little surreal, but I was in the Exploration Systems Design program here at ASU, which is really meant for people that want to build instruments for astronomy, for cosmology, for planetary science, geology, what have you. I was loving seeing you guys' eclipse photos. I did not travel to see this eclipse, but I was fortunate enough to live in Nashville in 2017. And so I threw this picture in here. This is me and my dad at the Vanderbilt campus event for that eclipse. It really is amazing to see. And if any of you guys didn't see totality this time around, definitely try and see it once before. It's really incredible. All right, so I'm currently a postdoc at ASU. I work in the Astro and Cosmology Instrumentation Group with Rick Scott and Tom Marsden. All right, so I'll jump right in. I do not consider myself to be an astronomer by any means, but I'm here to talk to you guys a little bit about cosmology. Oh no. Okay, well, hopefully all of my slides are not formatted incorrectly, but we'll get through it. So anyway, so this figure is kind of showing the evolution of the universe over time. So in the Big Bang theory of the universe, everything started out as kind of this unimaginably hot and dense soup of fundamental particles, plasma, like we heard about earlier. And about 380,000 years after the Big Bang happened, the universe finally cooled. It had expanded enough and things had cooled down enough for matter and photons to kind of disentangle from each other. And the photons began traveling all across the universe as it expanded. And as they did, they became cooler and cooler in temperature, and their wavelengths were redshifted to longer wavelengths. And so today, we see these photons as kind of this uniform background glow that we call the cosmic microwave background. It's around 3 Kelvin approximately average temperature. But if you have a really nice fine detail map like this one from the Planck satellite, you can actually see that there's regions that are a little bit hotter, there's regions that are a little bit colder, and these are very, very, very small scale fluctuations in temperature. And these arise actually from the initial conditions of the Big Bang. So the more we can find out about these fluctuations, the more we can kind of learn about what the very, very early universe was like. Okay, all right, I guess all of my headings are just gonna be, it's fine. So observing the cosmic microwave background, which is this orange kind of shaded region here are the wavelengths, the CMB, is difficult to do from the ground, mainly because our atmosphere gets in the way. And that's true of a lot of wavelength regions in the electromagnetic spectrum. You guys enjoy your optical telescopes because we have nice windows where you can actually see things. And radio astronomy is pretty easy to do from Earth. But a lot of the CMB, millimeter, and high energy experiments, you would prefer to have your telescopes in space to get above the atmosphere and really be able to see the light. And so other options, instead of going to space, because going to space is really expensive, we have things like high altitude balloons. So my PhD advisor, Phil Mauskopf, was on the Boomerang experiment, which is a high altitude balloon that flew a telescope above Antarctica. That's one option. You can do kind of a short-lived observing mission that way. Also, we have things like SOFIA, which was an infrared telescope that up until recently would fly on an airplane. They would do flights and observe that way. So for the CMB, we have a few little windows that we can exploit if we get above as much of the atmosphere as we can. So you put your telescope on a very tall mountain and preferably in a very dry area. So you get less of that water vapor that also prohibits you from viewing the CMB. All right. Speaking of SOFIA, just a quick sidebar. I don't know how many of you guys have been to the Pima Air and Space Museum, but it is now, the aircraft is now on display there. And so my dad and I, my dad is a huge airplane nerd in general. I don't know if there's any of those here. We went a few weeks ago and it actually happened to be open, the interior, so you could go inside and see. That was super cool. It's a really cool piece of kind of space history to have here in our backyard. Unfortunately, the telescope itself was retired to a different museum in Germany. So if you want to see the whole thing, you'll have to make 2 different trips. But I definitely would recommend the day trip down to Tucson to see this piece of space history. Okay. All right. I do not know. Okay, so the Atacama Desert is one of the highest and driest locations on Earth. And so it's really great for observing the cosmic microwave background. And historically, a lot of the experiments observing the CMB have been sited in this small region in Chile. And so in this area, the Andes Mountains are upwards of 17,000 feet in elevation. And this is the driest desert on Earth, excepting some regions of Antarctica. And Antarctica is also kind of the other preeminent location to observe the CMB. We have the South Pole Telescope at the South Pole that observes the CMB, as well as a lot of balloon experiments that launch from Antarctica. However, Antarctica is pretty difficult to get to. Comparatively speaking, Chile, I was talking to some folks just a few minutes ago. It's a 24-hour door-to-door trip, which is a long slog, but it is much easier to get there than it is to get to Antarctica. So it really is a great place to kind of set up these large-scale observatories. We also have really cute wildlife. I've interspersed photos of the furry friends I encountered in my time in Chile throughout this presentation, just for an extra dose of cuteness. But yeah, so this photo was taken from San Pedro, which I don't know if any of you guys have ever been to the Atacama Desert. That's probably the most popular town in the region. So this is looking out towards the mountains, and that mountain in the center is Cerro Toco, which is where our observatory is. And so this photo is taken from atop Cerro Toco, and we have here in the background off to the right, we have ALMA, which I'm sure some of you guys are familiar with. Many different antennas of ALMA are off there in the distance. And then back here in the middle, that tall mountain there is we have the Tokyo Atacama Observatory, which is at 18,500 feet, and that's currently the highest elevated observatory in the world. And then just below that, at around 17,500 feet, we have currently we have Polar Bear and Class, which are two other CMB experiments. And then we have here in the front the Atacama Cosmology Telescope, which was just recently decommissioned after over a decade of great observing and science. And then we have this area down here in the bottom right, and you're like, man, you could put a few more telescopes there. It's like nice flat land. And so that's what we're doing for Simon's Observatory. All right, so here's looking the other direction. So in this photo, Alma and Tao are behind the camera, and then we have our three platforms here for our small aperture telescopes. They're 1/2 meter telescopes. And then up here in the front, we have our 6 meter large aperture telescopes. So we have 4 telescopes in total. A mix of small and large apertures gives us a wide range of angular scales. And back here, we have ACT and Polar Bear and Class, so you can kind of compare to the previous image, kind of orient yourself. All right, so here's the CAD rendering of our kind of suite of telescopes here. This is a very large collaboration, over 300 members from around the world are part of this collaboration. So like I said, we have these 3 small aperture telescopes. Each one of them kind of looks like that receiver there. They go inside of this ground screen. And then up top, we have our large aperture telescope receiver. So this receiver here is basically a giant fridge that contains 30,000 detectors in itself. And then the small aperture telescopes are quite a bit smaller, but they still all have lots of detectors as well. But like I said, I've been working on this project for quite a while now. And so I've been fortunate enough to see kind of the development from CAD drawings and designs and blueprints to actual real things in real life. So on the right here, we have the photo that we all took after we got that large aperture telescope receiver lifted up into the cabin there. There's the whole team. I don't know, maybe kind of the same scale as the photo we had in the previous presentation of the coils. Very large things. And then we have the small aperture telescope. One of them we have there down in the bottom. All right, so the Simon's Observatory is kind of a big stepping stone towards the next generation of CMB experiments. So we're not very creative in our naming schemes, but traditionally, CMB experiments have been grouped into just stages. So we had like stage 1 experiments where in the very beginning they had maybe like 8 detectors and they were very, small experiments. And then we've kind of been building up. And so this figure here just shows kind of as the years have gone on, our sensitivity and our measurements of the CMB are going down, and the numbers of detectors that we're fielding in these experiments is going up quite exponentially. And so Simon's Observatory is on kind of the tail end of stage 3 of CMB experiments. So we have over 60,000 detectors in our initial phase of operations, which is an order of magnitude more than all of the previous experiments have had combined. And so they're distributed across 6 different frequency bands. And then we have, of course, some in the SATs, the small aperture telescopes, which are specialized in the degree scale observations. And so their primary goal is to look for kind of the smoking gun evidence for inflation or B mode polarization of the cosmic microwave background. And so they're looking for evidence of primordial gravitational waves, and people that are much more nerdy about cosmology could tell you all about that. I just built the things, but we also use small aperture telescopes to get really quality images of the systematics and the foreground light and other contaminants so that we can remove them from our other observations. And then we have the large aperture telescope, which, like I said, has over 30,000 detectors in it. It's going to do the really high resolution images of the cosmic microwave background. And so that's going to allow us to do a lot of really great fundamental physics and particle physics and galactic science, large scale structure studies, lensing, all of this that kind of runs the gamut of cosmology. All right, and so we have up at the top one of the many street dogs of San Pedro. But these are the detectors that we use. They're called transition edge sensors, and these are the current state of the art for CMB experiments. These are superconducting detectors that are operated at extremely cold temperatures. So we cryogenically cool them to around 100 millikelvin, which is like minus 450 degrees, something crazy. And these superconducting detectors convert changes in temperature. So because they're extremely cold, when you point them at the sky and they absorb these photons, their temperature increases a little bit. And so because they're superconductors, they take this increase in temperature, and that is processed as a change in a current through a coupled circuit. And so we exploit that in these large format arrays. To this array down here at the bottom is approximately 1,700 detectors, and this is about the size of my hand. And so these are photon noise limited detectors, which means that the main source of noise in these detectors is just the random nature of photons as they arrive at the detectors. So the best way to increase the signal to noise is just to have more detectors. And so that's why we pack them into these arrays. But then when you have all of these detectors, it becomes difficult to read them all out simultaneously without having, a monstrosity of electronics and cables and wires and things that will make it really hard to keep the detectors cold, because you have to cool all this stuff in stages. And so you want to keep the associated electronics kind of simple in order to still be able to achieve your base temperatures. Okay, so I'm not going to get super in the weeds here, especially because it's all covered up, but for people like Rick, I know, are interested in this kind of engineering stuff. But we are able to read out on order 1,000 detectors per single set of cables coming out of the telescope. And we do that by tethering many of these detectors to a single transmission line by coupling them to microwave resonators. And so these resonators each have a distinct resonant frequency. And when the transition edge sensors detect photons and they have current changes, the coupled microwave resonator has a specific resonance frequency, but when we have the detected light, that resonance shifts a little bit. And so we're able to kind of detect these signals by using very complicated tone tracking hardware and software that sends known signals through the system and analyzes the change in that tone as it comes back out. And so here is a diagram of what the whole system looks like for this experiment. And so there's a lot of parts. Up at the top, we have that diagram that I had on the previous slide. This is all the detectors. And over on the left there, you can see the same photo of the detector array in the middle. And then up at the top, we have basically that's the hardware version of that circuit that you see on the right. And so we couple those together along with on the bottom, we have our optical coupling elements. So little tiny lenses or little tiny antennas that actually focus the light onto the detectors themselves. We package them all together in this hexagonal box that you see at the right. And we call those focal plane modules. And so those are all at 100 millikelvin. And then beyond that, as you go down here, you're getting warmer. And so at 4 Kelvin and 40 Kelvin and 300 Kelvin, we have these 3 plates that you can see in this assembly here this is what we call the universal readout harness. And this was the crux of my PhD work, was assembling these together. So this is kind of a modular assembly. You just kind of plug it into the side of the telescope. And this has all of the cables and components that are required for those 3 temperature stages. And then down at the bottom here, we have the warm readout. So this is outside of the cooled portion of the telescope. This is what does all of the analysis of the signals and all of the tone tracking and resonator tracking and all that kind of stuff. This was developed by our colleagues at the SLAC over in Stanford, and they called it the SLAC Micro Resonator Frequency Electronics, or the SMRF. So, and then just for context, for the large aperture telescope, we use 45 sets of these cables that you see here. So 45 iterations of the blocks that you see there to read out over 300,000 detectors. So really, that's quite impressive because you're coupling, over 1,000 detectors per a single set of cables. Okay, so I'll talk a little bit more now about the universal readout harness, which was my work. So now you can see a little bit better these coax loops. So each one of these loops is kind of going from, this is room temperature here up to 4 Kelvin there, but each kind of set of these cables is one readout line. So for the large aperture telescope, we have 45 implementations of these little cables here. And we also have many other components that I'll call out here. So these low noise amplifiers here, these devices are actually fabricated by our group at ASU. We designed these specifically to meet the requirements of our system. And we have all of these cables down here at the bottom. These are fancy DC ribbon cables. These help us take power to all of the different components at all the different temperature stages. And then in the middle there, we have these red circuit boards. Those are breaking out some of those power lines to our amplifiers here so that we can operate them. And here's a close-up of one of the coaxial cable loops. These are hand bent by a Japanese company. And so a lot of my PhD work was twisting SMA connectors. A lot of fun. We also have, shiny tinfoil looking stuff. That's to help us keep our temperature stages cool at the appropriate temperatures. And then we have support rods that keep everything together while I'm assembling it on the bench. And then actually once we install it into the telescopes, we can pull them out because the plates themselves get bolted to different shells. And so that kind of limits the heat transfer that we get in between stages. And then when you have a system as complex as this, it's really important to be able to validate smaller portions of it at a time before you put everything together, because you have a lot of different parts. And so if you put it all together and then you test it and something doesn't look right, it becomes a lot more difficult to pinpoint where something's going wrong. So we built a test cryostat here at ASU in our lab, specifically to test these readout harnesses. And so a lot of my PhD work was building these things, putting them in this cryostat, and then cooling them down and testing all of the different cables and amplifiers. And down here we have, this was Dory. This is the house cat at the hostel that I stayed at while I was in Chile. She's very sweet. So anyway, so like I said, I was in Chile. After I assembled 6 of those readout assemblies and distributed them to my colleagues that were actually assembling these telescopes, I got to go down to the site in Atacama, and I spent 6 weeks there last summer. Summer for North America, it was winter down there. And so here's just some photos of my assemblies in the different telescopes. So this is the large aperture telescope receiver. So this houses all of the detectors and associated electronics for the 6-meter telescope. And, I saw one of my assemblies poking out the side there, how to get a selfie with it. You can see I'm wearing supplemental oxygen. I had some questions about that earlier. At that high of an altitude, you do really want to be wearing supplemental oxygen at all times. It is extremely difficult to work. Even when you have it, you definitely get winded really easily, but I can't imagine working up there without oxygen. Yes, ma'am. 17,500 feet. And then you can see here, this is the inside of the telescope. So these hexagonal places here, these are where the optics tubes go. So this houses all of the lenses and all of the detectors for the large aperture telescope. So they built them in these modular optics tubes. And then I was actually more involved with the small aperture telescope team, like I mentioned earlier. I spent a lot of time at the University of California in San Diego helping to assemble this receiver here. So I've got the red outline up there. That's my assembly kind of poking out at the top. And then we have here, this is the focal plane for the small aperture telescope. So here's my assembly here. And we get these long coaxial cable runs that go to the focal plane up there. And we have these other kind of ring structures here. These are the other, this is like the 1 Kelvin ring and the 4 Kelvin ring. So we do cool things in stages. And we have parts kind of at every stage. All right, so I was also tasked when I got to Chile with assembling everything that went in between kind of the outside of the telescope and the actual readout electronics, that SMRF system that I showed. So there's a lot more cables and amplifiers and wires and stuff that get mounted onto the side of the telescope and then get connected to the heavy duty readout electronics. So more fun with coax. You can't read what that says, but that's fine. It's a lot of these big blue coaxial cables. So this is what it looks like when we're set up in the lab to do lab testing of the telescope before we take it out to the site. Of course, when we moved out to the site, this stuff isn't just hanging off the side exposed to the elements. We have a lot of environmental enclosures that this stuff gets all tucked away in, a lot of ductwork to hide all the cables in. And a lot of this stuff just kind of gets mounted right on the side of the telescope. Okay, so here's some photos of the platform installation. So on the left, we have the SAT, so the small aperture telescope that was in the previous few slides. It's being dropped down into the platform. And then over here, we have the big receiver for the large aperture telescope being lifted up into the receiver cabin. This was a very fun day on the mountain, watching many different personalities attempting to guide a very large and expensive piece of equipment up into its place. But we had a great team. And here's just some more photos of the SAT there. You can see we have the 4 baffle installed now. And these are just some of the great people that I worked with. We took this photo after we installed all of the detector modules in the telescope in the lab. And then here's just kind of showing, so the telescope goes into the platform there, and then here's the ground screens. Just more fun pictures of the site. And then I know I told you guys it's like one of the driest deserts in the world, but in the past few months, they've gotten tons of snow. Which has been problematic, but also fun. We've had some snowmen get made. But kind of what's next for us is, so 2 of our small aperture telescopes are installed on the platforms. They've had first light observations. They've started doing test scans. They've been looking at the moon. They've been looking at Jupiter. They've been calibrating things and getting the pipeline running. The 3rd small aperture telescope is at the site. It's working on getting out to the platform as well. The large aperture telescope should have its first light early next year. They're waiting on the mirrors, but all of the associated detectors and stuff, they're all there already. They're waiting for the mirrors to direct the light to the receiver. But in the future, which is why I'm still here at ASU as a postdoc, is because we are expanding this observatory. We're not even fully operational yet in the initial stage, and we've already gotten funding to add more. Which is great for me, it's great job security, but we're adding another 30,000 detectors in our large aperture telescope. So it will have over 60,000 detectors just in that one big receiver. We're also gonna get 2 additional small aperture telescopes from the UK, and Japan is also gonna contribute another one. We're also gonna get a new photovoltaic array, so we will be going green. We're gonna be replacing a lot of the diesel power, which is great because it is usually super sunny up there on the mountain. But yeah, I'll leave you guys with this kind of latest photo of the site. I think this was taken late last year. It is really great. Like I said, as someone that started kind of when it was all still in the design phase, to see now everything existing in real life is really great. But yeah, if you guys have any questions, I'd be happy to answer them. And otherwise, thank you.
Questions for Dr. Moore?
So are the resonators in the little RF modules that you guys were built?
Mm-hmm.
So they're very small, and the cables need to be bent to a specific dimension because.
Yeah, so we have them in the specific loops because that helps with thermal contraction because they're connected to two different temperature stages. So having that, it's kind of becomes a spring.
What format is the data output? What do you wind up with?
So we will have maps of the CMB. So kind of like the map that I showed at the very beginning of the talk from Planck, with all the temperature of the CMB. So we have maps like that. We'll also have catalogs of different sources that we find with the Large Aperture Telescope. We won't necessarily, we won't output images like we saw earlier of specific things. It's a very different kind of data than optical or infrared. Yeah, so that's the big push. Yeah, we'll get that one next, sorry. The big push to have such a large telescope with such a large focal plane is to get better resolution.
What's the mechanism that you use to achieve those cold temperatures?
So we have helium dilution refrigerators that cool. I'm not a cryogenic expert, but it is helium cooled down to 100 millikelvin is our base temperature.
How's the telescope? How is the telescope for observing microwaves? Is that the same as a light telescope, or is it different?
So we have in the Large Aperture Telescope, we have mirrors that direct the light to the receiver, and then there's a bunch of lenses and filters. So in that sense, it's kind of similar. I would say probably our detection or our detectors are what's really different, and as opposed to something in the optical that maybe uses a CCD based detector, we're using something that is really kind of detecting photons on a very almost like an individual level.
Okay, forgive me, being an optical guy. You showed the hexagonal focal plane element that contains a large number of individual detectors. Is that hexagonal element analogous to 1 pixel in my CCD camera?
That's a good question. So each kind of, I'll scroll back to that photo.
Maybe. Yeah, that guy.
Yeah, so each little kind of dot in that hexagonal array actually has 4 pixels in it. And so this whole array in itself has around, I think, 1,700 total detectors. So that, I don't think it's, so you having 1 pixel, so this would be many more pixels.
Okay. What confused me about that is your comment about signal to noise ratio growing with the number of detectors.
Correct.
Which implied to me that in effect they're all summed into a single data.
No, they're, yeah.
Cool. And it's basically a reflecting telescope that's collecting the light. pointing at these detectors?
Yeah, so the large aperture telescope has mirrors. The small aperture telescopes they just have lenses.
Mm-hmm. Other questions? I've got a couple of questions for you.
Oh.
It was hard to tell in the pictures, but do these track or do they just permanently mounted and wait for the Earth to turn?
No, they have all of the platforms rotate. It's very I have videos which I wish I could share with you guys. I should have thought of that, but yeah. So the sats all rotate, and the whole platform rotates this way, and then there's also rotation in all of the different, as an L. The large aperture telescope receiver actually co-rotates as well. So we're not just staring at one point and watching the Earth go, or the sky go around. We definitely have lots of different ways that we can move and look at different things.
So do you have an idea of how much of the sky that you can actually cover?
So the large aperture telescope, I know off the top of my head, is going to survey around 40% of the sky.
Excellent. Other question is, did they put a pulse oximeter on your finger when you got up there?
Multiple times a day, yes. Someone came around and stuck something on my finger and said either, you're good to go, or we need to turn your concentrator up.
Did you see any vicuna?
Yes, I saw lots of vicuña. I had a few photos of them scattered throughout the presentation. And the other big animal that's popular, aside from the street dogs down in town, are viscacha, which are kind of like a cross between a rabbit and a squirrel. They got the nice big bunny ears, and they got a big bushy tail. But yeah, it's impressive that animals are able to survive up on that mountain. There's very little water, and it's a very harsh environment. But yeah, there are lots of animals.
Thank you.
Mm-hmm. Oh, we've inspired more questions.
Maybe you answered this already, but what is the aperture size of the LAT?
6 meters.
16?
6.
6 meters?
Meters, yes.
Okay.
We also have a couple online.
Oh.
The pulse oximeter reminded me. I have heard stories from Mauna Kea that the lack of oxygen affects your intellect and decision-making capability.
Absolutely.
Do you have any personal stories about that?
I did not, because I was fortunate enough to be wearing oxygen the entire time, but definitely from some of the senior staff that I was working with who, back when they were graduate students working up on the mountain, did not have oxygen. I think we've confirmed that theory. It very much affects your mental faculties.
So we got 2 online questions. The first one is, are there any open positions for C++ software engineer, highly experienced in HPC, to work on site at the Atacama Desert for the Simmons Observatory? I guess the question would be where to go.
Where to go? simonsobservatory.org. We do not do any of the software in our group. We do mainly hardware, at least for this project. So I don't have it in for you. I'm sorry. Okay. But yeah.
Next question. Is data collected and analyzed at the site or remotely?
A little bit of both. Right now we're still in the commissioning phase. So we've got people there at the site, testing things out and analyzing the data kind of as it comes. But ultimately it will be all remotely analyzed and as part of the big national supercomputing architecture. I think it's based in Illinois, maybe. But yeah, it's going to be a lot of data. So yeah, it'll live in a big supercomputer storage facility.
Last call for questions. Here we have another one.
Does the system have a built-in test capability for individual products?
What was that last part, sorry?
I was asking if there's a built-in test procedure for having that many components. I can determine which one failed.
The built-in test procedure is a lot of graduate students testing things.
All right, let's thank Dr. Moore again for coming in.
I have stickers. I forgot until right now, but if anybody would like a sticker for Simon's Observatory, I do have them here. put them up here.
We are done.